computer tools for to actually being useful, right? So I feel like this is something me and some of the other faculty talk about from time to time, that there's sort of like a lot of emphasis on theory and not as much emphasis on actual like application. So I wanted to just kind of work through an example with you that was based on something I did with a couple students in my office, and the more I thought about it, I thought it would maybe be worth burning like a third of a lecture on this because it's kind of interesting and it's useful. So, so first question, is everybody familiar with using matrices to solve systems of equations? Good. So, so for example, just in case you've forgotten, like if you have something like, 3x plus y equals, let's see, 1, 2, 5, and 2x minus y equals, hold on, what was in my example? 1, 2, 0. Then you could write a system of equations where you put, you make one matrix with the coefficients, so 3, 1, 2, negative 1. And then you make another matrix with the constants. So in this case, it would be 5 and 0. And then from a matrix standpoint, essentially what you're saying is that A times B, is that A times your variables equals B. So you can then say, you can solve for your variables by saying V equals B divided by A. Okay, and that's like standard. You can probably do it on your calculator. If your calculator is sort of has enough horsepower. You can do it in Matlab. You could probably do it in just about any other number crunching tool that there is out there, right? It's just like a standard trick. The actual software you use to solve it is sort of, besides the point. It's like standard matrix solving tool. Okay. In Matlab, the specific command that I'm gonna show you is you say A / B. Okay, and that will actually give you the coefficients. All right. So what does that have to do with circuits? Well, obviously, just about everything with circuits is a system of equations. So if I come to you and I say, I gave you like some boring DC circuits problem, like some of those ones that you spend a bunch of time on in circuits 1. So let's say I gave you something like this, the double voltage divider. Okay. You could easily set up a system of equations for this and then use the computer to solve the system of equations, right? So then, the problem would go from one that's kind of ugly because you'd be having like sort of the traditional way of doing it is to write the system of equations and then solve them by hand, right? And that's what makes all those chapter 5 problems god awful because, they put current sources and resistors going diagonally and, they cook up whatever nonsense they can and they sort of expect you to wail on it by hand. But realistically, it's just a bunch of pretty trivial equations, and if you can write that system of equations, you can stick them into any solver and get the right answer. Okay, and then it's sort of irrelevant whether or not you can solve a, 5x5 system of equations by hand, because really, no one's gonna you're not gonna go to a job where they're gonna say, "Oh, I got this 10x10 system of equations, solve it." I mean, that's not a real world skill, right? That'll take you like a half a day to do, and you'll probably make a mistake. And a computer could do it in about 1 second. So just to do the example all the way through, because in a minute we're going to, I want to do this so I can do the next example. If we call this V in, we call this V out, and we call this Vx, and then we've got R1, R2, R3, and R4. Let's see, how many equations do you think I'm going to have? 2? I guess it depends how you write it, huh? I mean, you could do a nodal analysis or a mesh analysis. You're right. So let's do, yeah, actually, I think 2 equations will work for this. Right. So I always like to do the the current equations across the resistors. That works for me. So I would write that V in minus Vx over R1 equals what? That's going to be Vx over R2 plus Vx minus V out over R3. Okay? You with me? Okay, and then what's my other equation? Right. Right, I've got to say that this current equals that current. So that would be Vx minus V out over R3 equals V out over R4. Now, when you go and sit in old Sullivan's class, and I'm not saying this is a thing on Sullivan, but like, the plan of the strategy is solve both equations for Vx, set them equal to each other, right? Fill a page full of math, and then, hope that you didn't lose a minus sign somewhere, because then your life will be miserable, okay? So, let's do the grown-up way. I mean, I guess the really grown-up way would just be to draw it in a circuit simulator and get the answer. That would work too. And I don't think it would be any less wrong. So here's what I'm going to do. I'm going to tidy up both of those equations just a little bit. So let's see here. I think what I'm going to do on the top, let's see here. So what are my unknowns? Let me just start with that. What are my unknowns? And what are my givens? Is V out an unknown? Vx? Yeah, what about V in? No, I'm supplying that. Okay, so let me start by cleaning up the top equation. I'm going to multiply through by R1. I'm going to multiply through by R2. So basically I'm going to clean up, I'm going to get rid of my denominators. And then I'm going to multiply through by R3. Okay, then I'm going to get all the unknowns on one side and all the knowns on and all the givens on the other side. So if I get all the unknowns on one side, holy cow. Well, this is turning into a mess. Maybe I should do an intermediate step just to tidy this up. So let me just distribute everything. So I've got R2, R3, V in. Is that right? Minus R2, R3, Vx equals, help a guy out here, R1, R3, Vx that was the middle term. All right, plus R1, R2, Vx minus R1, R2, V out. Okay, so I want to rearrange that so all my unknowns are on one side. So why don't I do this? Why don't I say something clever like, okay, so why don't I rewrite this as Vx times R1, R3 plus R1, R2 plus R2, R3. So that was bringing that term over there. Minus R1, R2, V out. And that's going to equal R2, R3, V in. Is that good? Seriously, you should stop me now before I, in case I've lied to you. We okay? I think we're good. All right, now we're going to play the same game for the other equation, which mercifully is a little cleaner. We multiply through by R4. We multiply through by R3. And that equation is going to be, it looks like R4Vx. So Vx R4 minus, or rather, I want to keep everything as a, okay, so minus, it's going to be R3 plus R4. Is that correctly grouping those together? For because I've got my VXR4, and then I brought this term over to this side, so it's minus V out R3 minus V out R4, which I just grouped together. So that's going to equal what? 0. It's going to equal 0. Do I have a system of equations? I do. Okay, 2 equations and 2 unknowns. All right, so what's my A matrix? It's just the coefficients, right? So the A matrix is R1, R3 plus R1, R2 plus R2, R3. I put an R4 down here. Then I've got a minus R1, R2. I've got a minus R3 plus R4. So that's my A matrix. And what's my B matrix going to equal? Careful. R2, R3, Vn. You got to include the Vn, right? Because that's a quantity that you're being given. It's not a coefficient. It's a number you're supplying. And then that's 0. All right, should we try this? Again, I know this seems like a lot of work, but basically it's just manipulating fairly straightforward equations, right? I mean, I think that you'll agree that this is hopefully a little easier than actually trying to solve the system. And this has the added advantage that I hope, we can manipulate this to be a little more flexible. So, plus we're going to learn a little bit of Matlab in the process. Okay, that looks like it's going to turn on. See if my computer... No. Oh. There we go. Detect displays. My computer does not like talking to projectors. Okay. I think we're good now. And let's just pull this up while we're waiting. Textbook. Okay, let's see. I'm going to kill a couple lights. There we go. Okay, so watch how straightforward we can do this. Okay, so let's pick a value for Vn. I don't know, 1 volt. Let's see, clear. Start by clearing the memory. So let's see, R1. I'm just going to start by sticking in values, okay? And then we can change those values. R1 equals 1, R2 equals 1, R3 equals 1, R4 equals 1. And that's all of our unknowns, right? So now I define my A matrix. I'm going to go right off the menu. R1, R3 plus R1, R2 plus R2, R3. Okay, then I got to do minus R1, R2. Okay, now I got to do a semicolon in Matlab. A semicolon says go to the next line of the matrix. And the 3 dots says you can continue on the next line of the text file if you wish. So then I've got R4, and I've got minus R3 plus R4. So minus R3 plus R4. Okay, so that was easy. My B matrix is going to be R2, R3, V in, R2, R3, V in, and 0. And finally, I'm just going to say X equals A back divide B. Display X. I'll post this code online. Okay, so here's my answer. Done. So you'll see that setting up the equations took a little bit of work, but the advantage is that we didn't actually have to solve that system, right? We leveraged the power of the computer. And I hope you'll believe me that this is about the hardest case you might even dream about doing by hand, right? For all those other problems that you looked at in circuits where it was really like a lot more components and there was dependent elements and so on and so forth. This is way easier to do, right? So I've got a 0.4 and a 0.2. What's the 0.4 tell me? 0.4 is Vx, and 0.2 is V out. We know it's Vx because we put Vx first, right? Vx was the first variable and V out was the second variable. Those numbers make sense? I think so, yeah. I mean, this one should always be, this one should be, there should be a voltage divider between, to get you to V out from Vx, so that works. We can always test it. What would happen if I set R4 equal to 0? What should I get? Looking at your circuit. Looking at the circuit. Right, if you set R4 equal to 0, what's your output going to do? Your output should short to 0. Let's try that. Boom. That's a good sign. All right, what happens? What should we get if we set R2 equal to 0? Let me redraw the circuit here just so that we can all be on the same page. Actually, no, let's do this. So it's R1, R2, R3, and R4. What if we set R2 equals to infinity? What should my output voltage be? Like if I basically take that resistor out. If I take that resistor out, then this voltage should just be a voltage divider, right? At 1 over 1, 2, 3. Okay, well I can do that, right? I'm just going to set R2 equal to infinity. Oh, that's weak. Okay, how about I just set it to some really big number? There we go. A third. That's nice, right? Isn't that easy? So now you can change all the values you want and the computer will just solve it, right? You don't have to keep doing it over and over by hand. Now, I told you this story to tell you an even better story, okay? If you're using a sufficiently sophisticated tool like Matlab, and if you happen to switch from working to DC sources to phasors, what changes? Your resistances turn into impedances, but mathematically, it's all the same, right? Instead of solving a system of real equations, now you're going to solve a system of complex ones. But the computer doesn't care. It's just going to work all the same. So let's look at an example of a problem that's just a nightmare to do by hand and a piece of cake to do on the computer, okay? And that's what I want to teach you is like the value of learning these stunts by hand. So let's look at problem 817. Again, I do apologize for sort of looking at material that's a little behind where we are now, but I just saw this and I thought, well, this is a cool problem. Like we should totally do this. This is worth the time. So this looks a little familiar to what we've just done, right? It's the same 4 components. Find the value of the capacitance so that I of t, that current, will be in phase with the source voltage. So my source voltage is 60 cosine 250t plus 30 degrees. All right? 60 cosine 250t plus 30 degrees. Now, I'm going to get a current here. Depending on the value of the capacitor, that current may have a phase angle of 30 degrees or any degrees, right? It could be 0 degrees, -5 degrees, whatever degrees, okay? So the question is, can I pick a capacitance that will give me a current that is in phase with my input? Would anyone like to do this by hand? Ew, right? Total nightmare to do this by hand. I mean, at very best, what you'd have to do is get an equation for I of t as a function of c, and then figure out what value of c would give you the phase that you want. I mean, it could be done, but you're going to spend a lot of time on it. So I have a better idea. Why don't we use our existing mechanism to figure this out? All right? And we don't even have to change hardly anything that's on the board. So let's start with our input. in a phasor notation, what is my V in? 60 angle 30 degrees. So far, so good. Okay. What's my frequency? 250 radians per second. I screwed this up the first time I did this, and I got the wrong answer for reasons that baffled me. 250 radians per second. Good. All right, according to our... So what I'm going to do here, all I want you to do is, instead of seeing R1, R2, R3, and R4, I want you to see Z1, Z2, Z3, and Z4. Okay? Doesn't change anything, right? Instead of R's, we're going to write Z's. Good. So let's see. What is Z1? 8. This is fun. Okay. What is Z2? It's 1 over J omega C. Okay. Which we can also write as minus J over omega C, where omega is 250. Z3 equals 15. Okay, even I can do that. And Z4 equals J times omega times L, which is 40 milli, right? 0.04. Somebody want to be a champ and multiply those together for me? 10. 10J. Pretty sweet, right? Okay. So here's what I'm going to do. I'm going to go and edit my code ever so slightly. So I'm going to change my Z's, my R's into Z's. You know what I could just do? I bet I could do replace all. Find R, replace with Z. Okay, that was easy. Okay, so we said Z1 was 8. Z2 was minus J over omega C. Okay, well, I'm going to leave it as omega C for now, just to kind of illustrate a larger point. Okay, so we'll do that. Z3 was 15, and Z4 was J omega L. So the reason, I mean, I could just fill in the numbers if I want, but the reason I like to do this is that I like to just show that you never want to do any more work than you have to. I mean, I totally could go and write 10J for Z4, but I kind of like to do it this way because then I really don't have to get my hands dirty. And if I decide to change my frequency for some reason, then I just change my frequency and I don't have to redo the calculation. Okay, so I know that omega equals 250, L equals 40 millis, and oh, what does C equal? We don't know what C is. So I'm just going to stick in a value. Okay? So let's just say 1 microfarad. I have no clue that that's the right answer. I'm just sticking it in as a placeholder so I can run this thing. Yes, sir?
L be 40 negative 3?
Yes, it should be. Thank you. Okay. Oh, what do I still need to fix? Vn. Thank you. So what's Vn going to be? Oh, look at this. It dealt with my Z. Okay. Okay. So Vn needs to be 60 angle 30. That's a complex number, isn't it? Okay. So how am I going to do that? How do I enter complex numbers in Matlab? Well, there's two ways. One way is I could convert it into a rectangular form, which is a bit of a drag. There's another way which works pretty well, which is, I don't know if you would have learned this, but the shortcut is 60 e to the j omega, j times your phase angle. But the phase angle's got to be in radians per second. So it's 30 pi over 180. What's that? It'll do j. it's not thrilled about it. Like if you mouse over the complaint it's giving me, it says replace complex I and j by 1i for speed and improved robustness. I just tend to ignore. Yeah, it'll let you do that. Alternately, you could say something like, that's one way of doing it. The alternate way is to do, hold on, let's see, help pull to cart. I think that's right. What is theta? Is theta in degrees or theta's in radians? Okay. So the other way you could do it is to say something like, forget it. Let's just stick with that method. Okay? So this is a roundabout way of creating my complex number. Again, if I didn't want to do that, I could have figured out that the real part of this is what? 60 cosine 30. And the imaginary part is 60 sine 30. So I could have just said 60 cosine 30 plus j 60 sine 30. I could have done that too, and that would have worked, you know, that would have worked exactly the same. So maybe that I'll do that as my alternate. I'll comment it out just so that, so I could have said 60 times cosine of 30 plus j sine 30. Yeah, what does the d do for me? Degrees, right? Cos d of 30. It actually knows what that is, right? You don't have to convert it to radians. Have a nice day. So either one of those will work. There we go. Let's put that one in. All right. So I'm going to go and solve. And it gave me that. What am I looking at? Well, yeah. I mean, let's start. So I solved my system of equations. First of all, that was cool, right? You want to do that by hand? No. Okay. Complex system of equations by hand, not so much fun. This, not so bad, right? It didn't care. You add complex numbers, divide complex numbers. I know you know how to do it, but it's time consuming, right? This is why I I say figure out how to do complex numbers on your calculator. You could save like 15 minutes on an exam that would otherwise be, riding on the treadmill of complex numbers. Okay, so whatever. I got these two numbers. What do they mean? That's got to be Vx, and that's got to be Vout. Okay, what do I do with that information? Am I any closer to my answer? What am I trying to figure out? The phase angle of the current. So, can I use these values to calculate my current? Totally. What's my current going to be? In Phasor notation, what's my current going to be? Yeah. Yeah, it's going to be Vin minus Vx over Z1. Is it not? And the beauty of this is that even though I'm dealing with phasors, I don't really care because the computer is going to handle all the complex numbers, right? I just need to write the equation and let the computer crunch the numbers for me. So my current, the one that I'm interested in, is Vin minus Vx over Z1. So let's calculate that. Okay, so sure, you've calculated, so let's do this. So it calculated x is the value it returned. So we'll say something like Vx equals x of 1, Vout equals x of 2. So I'll actually extract my answers. I'll extract my results from my matrix calculation. And now I can say something like I equals Vin minus Vx over Z1, display I. Okay, there's my current. What do you think? Is that the right answer?
No.
I don't know either. What am I trying to figure out? The phase angle of this, right? So this gave me my current as a phasor, but it expressed that phasor in complex. Why are we reaching for our calculators? We're going to make the computer do the work. It's like the one time you don't need to reach. I mean, you reach, fine, whatever. Okay. But the point is, let's make the computer sweat the details. So I would like the computer to express this number. I just want to look at the phase. I don't even care about the magnitude. I just want to look at the phase. So how can I get the phase of this? Yeah, there's a built-in function that does this. Please just display not I, but the angle of I. Okay, there's the angle. What units is that? Angle gives me radians. So I do need to do one more thing, which is convert it to degrees. So to convert it to degrees, I'm just going to take that angle, times it by 180, divide it by pi. Now I got 6 degrees. So for this arbitrary capacitance that I picked, and I told you I was just picking that capacitance out of a hat, I got a phase angle of 6 degrees. What do I want my phase angle to be? Not 0. I wanted it to match the phase angle of my input, 30 degrees. So what am I going to do now?
Raise the capacitance.
Yeah, I'm just going to start messing with the capacitance until this gets to 30. Yeah, you laugh. You try doing this by hand and we'll see who gets faster. So, first thing I'm going to do, I'm just going to multiply this by, I don't even know what direction this is going to go in. Okay, but I'm going to, just to find out, I'm going to multiply this by 10 and see whether this number gets bigger or smaller. Okay, and that will at least tell me how to go. Okay, so I'm going to change it from 1 microfarad to 10 microfarads. Got closer. Let's go up to 100. Ooh, now it's really close. Okay, so just to repeat what I just said, the first thing I even had to establish was what direction to go with the capacitance. Do I need to make the capacitance bigger or smaller? I multiplied it by 10, and I saw my phase angle got bigger. Multiplied it by 10 again. It got bigger yet. Okay, should I multiply it by 10 again? Too much. Okay, so now I can back off. All right, let's see. Do I want 200? Still too much. 150? 125? Woo! 123? Bang. 124? Now we're splitting hairs. And that's the right answer. That's the answer that the back of the book gives. Isn't this badass? I mean, seriously. The alternative, like, seriously, I defy you to do this problem by hand and still have the will to live. Okay? It's not pretty. Okay, but this is an engineering way to do this problem. Now, there's like a whole different level to this, which I'm not prepared to get into today. But, so we set the problem up, but then the task of getting the capacitance was basically trial and error, right? That was just me guessing numbers until I got an answer that made sense. So there's actually like a whole different layer to this, which is called the optimization layer, where there's actually algorithms where you can say to the computer, this is my function. I want you to keep messing with this number until this answer gets to 30. Okay? Because that could be very sophisticated. In fact, it may need to optimize, like, what if the number 40 hadn't been given? Okay? Like, what if I didn't give you the inductor or the capacitor? Okay, then it would need to, like, vary both of them in some sort of strategy, like in some sort of coordinated way, until it got an answer that gave the degrees of 30 for the current, right? So that would require some sort of strategy that was hopefully a bit more sophisticated than trial and error. So there's a whole different layer of this, which is once you've written the equation, you can then pass it to an optimizer, and the optimizer actually goes through does the work for you of the trial and error, to actually get the number that optimizes that equation or maximizes it or whatever it is you're trying to do. But it's pretty cool, right? I mean, it just works. And if I made this circuit more complicated, if I added another capacitor or another inductor, okay, you'd shrug. You just, well, there's another equation to add, right? Your system of equations, instead of a 2x2, would be a 3x3. Okay, so you make it a little more complicated, and that's it. You run it. Can I change my current? Like, I can change my frequency. No muss, no fuss. Right? I can change circuits. Like, I can redo this problem for any kind of, I can change any parameter I want, and it's trivial to get the right answer again. So this is some real engineering ninja stuff here. Okay, this is the deal. Questions? Yes?
Does Matlab have any built-in templates for different circuit designs that already have?
That's a good question. I don't think so. It's not a bad question at all. There is a Matlab circuit simulator in Simulink that I have not messed with. Or like I messed with it once and I'm like, oh, this is, it looked like more trouble than I wanted to get into. You might look into it. But I think it's the same thing. Like basically you've got to build it by hand. I'm actually willing to submit, though, that this solution is probably easier than building a circuit simulator. Because if you did it in a circuit simulator, like if you went to Multisim, for example, to solve this problem, you could build the circuit, and you could still do the trial and error thing with the current, but you'd still have to, after each simulation, measure the phase angle of the current and see whether it was 30 degrees. There would still be like that whole extra layer, whereas here it's just computing it for you naturally. So this actually might even be easier than a circuit simulator approach, which I think is pretty neat. Yeah?
Similar question with the circuit lab.
Yeah.
Can you do that? I mean, does it add the matrix functionality?
Well, no. The circuit lab doesn't have the matrix functionality, but you could just simulate it, right? You could just simulate it and keep varying the capacitance and simulating it until you got an answer that was the one that worked. But I still feel like mechanically this is probably a little easier to deal with. In fact, well, I will give you this, though. I'm willing to bet that if you could look under the hood on Circuit Lab or Multisim or any circuit simulator, I mean, how does it know what the answer is? It's doing this, right? I mean, if you were to write a circuit simulator, there would be the graphics layer where you actually like drag and drop the circuit elements. Then there would be another layer where it takes those circuit elements and makes a system of equations, right? Which I don't think is too hard to do in terms of like, if you have the circuit elements and you know what connects to what, you can probably automate the process of building a system of equations. And then a third layer where you solve the system of equations. So almost certainly under the hood, Multisim or Circuit Lab or whatever is doing this, right? It's just that it's shielding you from this process because this is kind of a drag. From some point of view, you may not want to do this calculation every time, but that's the calculation that's being done to get the answer. It's pretty cool, right? I mean, maybe I don't get out much, but I think that's pretty cool. Questions? All right, well, good. I think I might put this as a lab next year or something, like a homework. Okay, good. Well, I think that worked out pretty well. Yeah, and just for the record, if you decided that what was this, mesh or node the way we did it? I can never keep them straight. This is node. If you want to do this with mesh, it would work exactly the same way, right? Instead of solving for Vx and V out, you'd solve for I1 and I2, but mechanically it would work exactly the same and you'd get exactly the same answer. Okay? Good. Now what am I going to do with 10 minutes? Seriously, what am I going to do with 10 minutes?
Can you do one of the test problems?
Yeah, actually, I think that's a good idea. We'll save the power stuff for Wednesday. Incidentally, you need to go?
No, I didn't take the test.
Oh, snap, I forgot. Yeah, you're done. I forgot. Can you stop by sometime? take the test? When's good for you?
I was out of town.
No, I know. Just don't forget to take it. That's all I'm saying.
No.
Okay, well, while Mike is packing up, we do need to finish chapter 9 chapter 9. Is 9 the one we're doing now? Yeah. Please, if you haven't already, read to the end of chapter 9. There's a bunch of equations. I'm going to hit the highlights in class on Wednesday. I'm not going to go through word by word of that chapter. I'm going to assign you a homework set. That homework set will get posted tonight. So basically, we'll give you an example working through some of this power calculations. None of it's like rocket science, but it's we need to understand it because you might take a power course one day. Okay, so let's look at the exam. Yes, sir.
If you want to open Simulink, just go to New and then Simulink Project.
I think that's right. I seriously, for all my Matlab Kung Fu knowledge, I've opened Simulink like twice in my life. I have like no operational value in teaching you Simulink. Okay, which one do you want to talk about?
The one with the value of omega to maximize the current.
Oh yeah. Where was that? This one. Solve for the circuit current. How do you maximize it? All right. All right, in phasor space, what's my current? I equals V over Z. Ain't that right? What's my V? In phasor space. 3 angle 0. Okay, what's my impedance? Now it gets interesting. Okay. It's an inductor and a capacitor in series. So what am I doing to their phases? Adding them. Okay, what's the impedance of the inductor? J. Omega. What's omega? 2 times 4. Okay, so that's 8J. The impedance of the cap is minus J over omega times a quarter, 0.25. So what's that? Minus 2J. If they're in series, you add them. So you get 6J. And in phasor notation, what's 6J? 6 angle, right, pi over 2. So what does that leave me with? A half angle minus 90. So what's my current? 1/2 cosine 2t minus 90. How do I maximize the current through this thing? Oh! I mean, yeah, we'll go nuts, but sorry, bad reaction. Okay, so J omega L minus 1 over omega C. What value of omega? So if I want to maximize current, what do I got to do to my impedance? Minimize my impedance, right? If I want big current, I want little impedance. How can what's the smallest I can make that impedance? The smallest I can make it is 0. I'm going to solve for omega now. Anybody want to guess what that's going to equal? 1 over root LC. And so, I mean, this is bananas, right? If you set your frequency equal to LC, or 1 over root LC, you'll have effectively 0 impedance. Does that mean you can have infinite current? Kind of does, actually, right? It's a resonant circuit, and you're hitting it at the resonant frequency. That's what that means, right? So that means that circuit has a resonant frequency, and you'll be stimulating it at the resonant frequency, and that current will just keep getting bigger and bigger and bigger and bigger. It's like pushing someone on a swing, right? You're always pushing them in phase. They get higher and higher and higher. At some point, some practical limitation breaks, like the kid falls off the swing, or the voltage source can't actually provide 10,000 volts of AC power. But mathematically, that's in theory that's what happened. The current would just keep getting bigger and bigger and bigger because you keep adding energy into the system in phase with the system. Now, you're certainly welcome to take the derivative of this and minimize it, and you get the right answer. I mean, eventually you would get this. But that's the time saver. It was only a few points at the end of the exam, right? It was just 10 points for that. I'll give you 5 for trying. Come on. Quit your bitching. Jeez Louise. I didn't mean to trivialize. I mean, it's a tricky problem. But yeah, I mean, I'll give you points totally. I'll totally give you points for setting up the derivative. I mean, it just turns out that there's a shortcut to that. I mean, the derivative would be. I mean, let me see. Does that work? If you take the derivative of the impedance, you get L. What is that? That's let's see. Hold on. You've got omega L minus omega to the negative 1 times C to the negative 1. So if you take the derivative, you get L plus 2 omega to the negative 2 c to the negative 1 equals 0. So that gives you, I feel like there's, did I lose a minus sign? Let's see. So that gives you 2 omega to the negative 2 equals negative L C. No, there's no 2 here. I made that up. Right, so there's no 2 here. I'm getting a minus sign I'm not supposed to be getting, but otherwise, I'm cautiously optimistic that taking the derivative of this thing and setting it equal to 0 would give you the same answer, but I seem to be having a bit of a temporary brain fart. Okay, any other questions on the test? I got 5 minutes left. I want to do this. How about that one? Sub in for omega, solve the phasor. Right? That's going to give you 10j over 50 plus 10j. Figure out how to divide it, magnitude and phase. What do you think about these ones? Elliot pointed out a great way of figuring out which one this one was. I didn't even think about this, and I wrote the damn test. This circuit has one feature that none of the other 3 have. Gain. Has a little bit of gain in it, right? How much gain does it have? 1 plus 3 halves. 2.5. Has a little bit of gain in it. Okay, so look at my 4 responses. Does one of those have a little gain in it? Plot A. Have a nice day. Okay, the first circuit was a high-pass filter with a cutoff frequency of 1,000 rads per second, which you can get by multiplying it. So 1,000 rads per second means either a cutoff frequency at 1,000 rads per second or a step function that rises with a time constant of a millisecond. Okay, let's see. So let's see. It's not this one. We ruled that one out. This is rising with not the time constant of 1 millisecond. This is oscillating. This is a low-pass filter with a cutoff frequency of 1,000. So there's that one. So that's 2, basically by inspection. Okay, now you're down to dealing with these 2. Okay, and you're left with plots B and C. One of them oscillates and one of them doesn't. So really, now you're just down to figuring out omega naught and zeta for both of those, and you're done. It's easy for me to do it this quickly because I already know the answer and I already sat and thought about this. But I'm just saying, like, in principle, it can be done if you're you're sort of hip to what to look for. Okay, I'll post these solutions. Elliot's going to be grading this week. Come back on Wednesday. We'll have more fun.